Cool.
Hello, I'm Amos, a software engineer in China. Today, I'm going to share a new feature of ClickHouse called projections. This talk will show what projection is and how it works in ClickHouse. Before I start, I will show a little more information about myself. I'm an active ClickHouse contributor with over 300 merged pull requests. I also do some question answering around the ClickHouse community, such as Stack Overflow, EasyList, and chat groups. I hold a PhD degree in database system. Currently, I work for a video sharing company in China called ClickHouse. My duty is to develop and manage ClickHouse. In this talk, I will first do a short introduction of the projection concept, and then followed by a demo showing how to use projection in ClickHouse. Then I've described three main constructs of how we implement projections in ClickHouse. The interesting part will be the process of query analysis. After that, I will list some comparisons and experiment results and finish my talk with a few ideas about future works. All right, so what is projection? Let's take a look at the quote from the VLDB CSTOR paper. Projections are groups of columns sorted on the same attribute. So basically, projection is a way of organizing columns. In fact, projections are column collections. It's not related to the SQL operation that selects columns. The main purpose of projection is to optimize query execution. It's somehow related to materialized views in that both are trading space for time. In ClickHouse, we define projections that select query, just like materialized views. It's a bit more powerful because it can support arbitrary functions and their arbitrary combinations to accelerate various kinds of queries. It also has a unique feature that allows reading data with and without projection in one query. Now we get a brief idea of what projection is. It's natural to ask why we need projections in ClickHouse. There are some well-known issues. First, ClickHouse stores data in LSM-like formats. It's called merge tree, and it has many features like skip indices and pre-aggregation. However, it can only have one way of ordering columns. Furthermore, in order to use pre-aggregation, ClickHouse provides a dedicated merge tree engine called aggregating merge tree, which, however, requires manual setup of the aggregating rules, and it requires tedious query rewriting to use pre-aggregation, and it's no longer possible to query detailed data. To tackle these problems, we introduce projections. It solves them in a clean and a consistent way. Projections can reorder columns, pre-aggregate columns without losing detailed data. It automatically boosts query execution without changing anything in query. It can be defined by SQL directly, just like materialized views, but guarantees consistency. And we don't need to worry about replications. It's a two birds, one stone solution, or maybe just more birds in the future. Now I hope I've made projections attractive. Let's see how it works in a real example. Here's a demo of some video analyzing workload. Let's create a table to demonstrate the power of projection. Let's call this table video log, which contains a datetime column with 20,000 rows per second. It has two ID columns with huge cardinality and a domain column with low cardinality. It also contains two measurement columns, namely bytes and duration, of a video frame. The table is partitioned by day and favor the user ID column with regard to column ordering. Now we will see this video log table to go through three use cases. Let's populate some data for testing. We can populate the table with the right data distribution, by using the table engine generate random. Let's generate a day of video logs. There will be 1.7 billion records in total. Now let's check out the first use case, finding the hourly video stream property of a given user today. We will filter by some user ID and then aggregate by hour. Since the table is sorted on user ID, index works perfectly. We end up only reading 32,000 rows in 17 milliseconds. It's only 4 granules of data to read. What if we need to find the hourly video stream property of a given device today? In this case, index fails to work and the query runs very slowly. It has to go over all rows to find out a few matched records, which takes more than 8 seconds. It's definitely not appropriate to run this query concurrently. To see how projection can help, let's add a normal projection called pnorm to speed up querying by device ID. The syntax is similar to defining a materialized view. We just select needed columns and specify the desired column order. To actually generate the data projection, we need to materialize it. It's like populating a materialized view as well. Then we try again with the same query. Now it finishes in 55 milliseconds, which is 153 times faster, with only 24,000 rows to read. Please notice that the query just runs faster without any modification. Let's see another case, finding the hourly video stream property aggregated by domain today. Since we don't filter anything, it has to go through 1.7 billion rows, which ends up taking more than 11 seconds. Although the aggregation performance is impressive, it's still too slow to use when rendering interactive dashboards. To make it faster, let's add an aggregate projection, PAG, to speed up this group by domain query. The definition of a projection is similar, but smarter. We just need to provide what kind of aggregate queries to optimize. Then it will understand how to pre-aggregate it without any intervention. Again, we need to materialize it in order to take full advantage of this projection. Let's try again with the same query. It now finishes in 29 milliseconds and reads only 5,000 rows. It's nearly 400 times faster. Not only do we scan less data, but also aggregate less data, which relieves both CPU and memory. Again, the query just went faster without any modification. So how does projection bring so much performance? Basically, there is no magic. We just trade space for time. So what about space consumption? We provide system tables to export such information for projections. Let's find it out via a table called system.projection_paths. The pnorm projection reorders columns and stores less columns than a video log table. It costs about 40% of the space of the video log table. The PAG projection pre-aggregates columns, thus consumes much less space. It's nearly negligible, about 0.0001%. Usually, aggregate projections cost less space and accelerate queries considerably, but it's still highly related to the data distribution and the actual queries. Thus, we still need to properly design projections in production. Here is a complete list of statements about projection. We can create, add, drop, materialize, and clear projection, just like what we did for indices. Let's summarize the demo before going into the implementation. In ClickHouse, projections have two types, namely normal and aggregate. Newly added projections only affect new data. To build projections for existing data, we need materialization. Queries can use projections without any modification and will be accelerated even when some data paths don't have materialized projections. Of course, we can add multiple projections, and the best one will be used to execute a given query. Now we know projections are quite handy to use. So how does it work? Let me show the main constructs of the implementation of ClickHouse projections. ClickHouse projection contains three main parts: definition, storage, and query analysis. Projection definition looks like materialized views with a little bit intelligence to infer types. Projection storage is like tables, but with parents. Query analysis is a little bit complex, but quite interesting. It can figure out whether a projection can answer a query and reconstruct the query pipeline to answer it fast and correctly. Projection definition is basically a CTAS clause. All aliases in the definition query will be expanded to a canonical form. It's required to store and analyze projections in a deterministic way. If group by clause is used, an aggregate projection is created, and the aggregate functions will turn into intermediate types that pre-aggregates data. There is no need to manually write long aggregating types anymore. Internally, the query will be planned to a proper stage to generate the correct pre-aggregated table schema. But in general, it's just a variant of CTAS, just like materialized views. Projection storage is backed by merge tree data parts. They live inside the base table as a subdirectory of parent parts. As we can see from the example diagram, projection parts don't have partition information. They reuse this info from parent parts. After we organize projections in such way, merge, mutation, and replication almost work out magically. We just need to settle down some special branches like checksum calculation and add some recursion to each process, such as sending projections parts before parent parts, etc. The basic idea is quite simple, so I won't go into details. Now here comes the fun part, query analysis. Let's use an example to work it out. Let's reuse the setup from previous demo. Suppose we receive a query that finds the hourly video stream property aggregated by domain today. We have the video log table to answer the query. We also have an aggregate projection, PAG, which seems to be able to answer the query. But how can we be sure? Let's split the query into stages. It mainly consists of 4 steps: reading from storage, filtering by where predicates, build column arguments for aggregation, and aggregates data at the end. We will traverse backward to see if each step can be answered by projection PAG. First, let's check the aggregation action. It requires start of hour of datetime and domain as key columns, then sum of bytes and average of duration as measurement columns. Because projection is defined by some query, and the column names are canonical, we just transform the input query in the same way and check if names are the same. In this case, we found that projection PAG provides all columns needed by this projection. So we have 2 start and hour of datetime directly provided by projection PAG. We have domain, and we have the 2 measurement columns. Thus, we found the potential matched projection. Let's continue to check the remaining actions. What about actions before aggregation, like the where filter? The where action looks like a tree-like structure called the action DAG. It describes how columns are computed from other columns. Here, we need to check if the final result column can be generated by some columns in projection PAG. We found that PAG provides a column named 2 start and hour of datetime again, which can be used as the input of this DAG. Thus, we don't need to check the datetime column as it is unused. Now we know projection PAG still matches the query, thus becomes a valid candidate. There can be other stages to check too, such as pre-where and row policy. The procedure is similar, thus I won't repeat this process anymore. After collecting all valid projection candidates, we will try to select the best one for current query. In order to do that, we will do index analysis for every candidate and catch the data which is about to read. Let me just select the projection. that reads the least amount of data. It is worth noting that we don't need to tell if the projection is normal or aggregate. Less data is always better. And we use previous catch result to avoid index reanalysis. If a projection is selected, we will extend the query pipeline so that it can read from both projection paths and ordinary paths. This is in case if projection is not fully materialized, and the pipeline will of course generate correct result without any performance penalty. There are many other interesting aspects to consider during query analysis, and all of them are listed in the projection PR. So please take a look at the projection pull request if you are curious. Next, I'd like to tell a bit more about consistency. Projection achieves full consistency in 3 aspects, which are insert, select, and mutation. When inserting one block of data, it will form all projection blocks, which in turn build a new data part with projections. During select, if a projection is used to answer the query, all parts will generate data from this projection, no matter if it's a real projection part or a pipeline that generates projection data on the fly. During mutation, we check if it breaks the dependency of any projection and will rematerialize it properly. As a result, we mutate parts together with their projections if needed. Okay, enough about implementations. Let's talk about the pros and cons of projections in ClickHouse. I will also show some experiment results of projections in production. The main advantage of projections is its usability. We don't need to worry about data consistency and replication. We can change table schema without breaking anything. We don't need to tweak queries to use the best projection. If some query runs slowly, just make a projection out of it and probably materialize it, that's all. However, it does have some limitations. Since projections are part-level entities, they cannot do aggregation over multiple parts. This might be less efficient when the aggregation key has very low cardinality. Besides, some use cases require storing only aggregated data, which is 1 year older. It's not supported because projections cannot live without parent parts. However, we can apply some tricks, such as using collapsing merge tree to analyze all base parts. In addition, projections cannot support joins because it can only be derived from base table. Although projections have some limitations, it's still better than materialized views and aggregating merge tree in many aspects. We have complete query analysis and allows non-blocking inserts with consistency. This is because projection can be partially materialized. For queries that require pre-aggregation, use either materialized views or aggregating merge tree in ClickHouse is not user-friendly at all. A new user needs to understand the detail of how ClickHouse aggregation works in order to write correct queries. Now let's see some experiment results from the real use case. We've already seen the power of projections in the previous demo. Here I'll just list some notable results of aggregation projection, because the effect of the optimization is highly related to both queries and data distribution. The dataset we use here contains 35 billion rows per day, and the projection aggregates data down to less than a million rows. As a result, we can see that the queries can finish in milliseconds instead of near a minute. On the other hand, since ClickHouse is a column-oriented database, we can build just one projection with multiple aggregates to optimize different queries, and each query will only touch the aggregates which are used. The speed up in latency of the query execution is related to number of aggregates. The more aggregates are involved, the better speed up we can get. In addition, ClickHouse can scale almost linearly when you use multiple threads. However, since we have already achieved very low latency via aggregate projections, the benefit isn't reflected in query latency, but instead, we use much less computational resources to execute queries. Thus, we can support running more queries at the same time. Although we can achieve impressive improvements by adding many aggregates to a projection, it's worth mentioning that different aggregation states varies drastically with regard to the space consumption. This slide shows the column space consumption of two aggregate projections in a table. Simple aggregates such as count, average, max consumes a few kilobytes after aggregating 1 million rows. Aggregates with data digestions like hyperlog and tdigest can consume megabytes, while exact aggregates like unique exact takes hundreds of megabytes. So it's better to avoid such aggregates and pay attention to the total space consumption. Total space consumption. In addition to these experiment results, I'd also like to share the real improvements from the aspects of applications. In Kuaishou, there are a lot of BI dashboards with many data sheets to render interactively. In order to make the rendering faster, we collect frequent dashboard queries via normalized query analysis and build multiple projections to pre-aggregate data. After that, dashboard rendering becomes much more interactive, from 30 seconds down to 1 second. Before building projections, some dashboards cannot even be rendered completely. The overall space consumption of all these projections is less than 20% of the base table. And we don't see any slowdown of data insertion and data merge. Okay, let's summarize what ClickHouse projection is. ClickHouse projections are groups of columns which are defined by queries and used by queries. It's implemented by materializing queries into pieces of reusable data parts in a consistent way. It is designed to be a better materialized view in ClickHouse. In the end, I will share some ideas about projections in the future. Currently, we only have two kinds of projections. It's possible to add more. One interesting idea is to build secondary indices via projection. It is because projections live inside data parts that can store the internal data pointers of parent parts. It's also appealing to build bitmap indexes via projection because we can already build bitmaps via ClickHouse queries, and we only need to extend the query analyzer to figure out how to utilize these bitmaps. Moreover, we can extend the projection to support features of real tables, such as column encoding schemes and skip indices. One important missing feature is to add a new type of projection that separates its storage out from parent parts, so that they can aggregate more data, use different storages, and have different lifetimes. In order to achieve this, we have to figure out how to deal with consistency. So that's all. Thank you for attending my talk. The projection feature is already available, and I'd like to encourage brave users to try it out, as it's already running in production for quite some time. If you have any questions after trying projection, you can reach me on Telegram or via email. Now, let's see if there are any questions in the chat room.